Hello everyone, welcome back. This video will be a little bit shorter. We're going to go over the last two examples in our handout. I'm covering rational function graphs. First, let's talk about what's going on here. We have what I call a complete problem, where we have to take this function here that's y equals x squared plus 6x plus 5 over 2x squared minus 50, and identify all the things that make it the key features of this graph, the restrictions, points of discontinuity, removable and non-removable, what's the domain, and what are the vertical and horizontal asymptotes, and if it has any holes in the graph. So let's dig in. One of the first things you're going to want to do on a problem like this is to graph the function first. So you see what it looks like, so you can maybe identify some of the things. For instance, I've looked at these graphs long enough to know I think I see a vertical asymptote. All right. Now, what you can do on Desmos is you can say, well, I know a vertical asymptote is x equals a number. And it looks like it's 5. And if I put x equals 5 in there, I'm going to notice that that graph does this, thing where it's trying to avoid 5. So that seems to be the vertical asymptote. And we can drag that up and down. And it looks like that's the case there. Now, the horizontal asymptote looks like it has one too, but horizontal is y. But you can see that the y equals 0, the x-axis, the graph crosses it. So that's not an asymptote. So we know it's a little bit higher. So maybe it's at, I don't know, 0.5 or something like that. All right, we can just kind of take a guess. Maybe the horizontal's at 0.5. And is there a hole in the graph? Well, those are kind of harder to detect until you factor and cancel some things out. But at least we can get a visual and know what this graph looks like. Let's see if we can get all the information from it. So I want to factor this graph here to be able to effectively cancel some things out and identify restrictions and all that stuff. So first thing I'm going to do is I'm going to look at my numerator and denominator. Let's start with the numerator. We got x squared plus 6x plus 5. That's a trinomial factor. And so we want to be able to come up with the two factors that multiply to give you that. So they're going to start with x and x because we have to have x squared. And the last two numbers have to multiply to the last number here, which is going to have to be 5 and 1. And 5 plus 1 is 6. So those are your two factors, x plus 1, 5, x plus 1. Those would multiply. The denominator has a GCF. Notice that 50 and 2 are both divisible by 2. So first we're going to divide that GCF out, and we'll have x squared. And then 50 divided by 2 is 25. But as you can tell, that's probably going to be factorable again. So I'm going to factor the x squared minus 25. Can you think about what that factors to? That's a difference of squares. So that's going to be x plus 5, x minus 5. So I'm going to write that cleaned up a little bit. Y equals x plus 5, x plus 1. And then I'm going to put that over 2, x plus 5, x minus 5. Now we're ready to kind of get everything we need to get from this graph. So the first thing I want to do is identify the restrictions. So the restrictions are what makes your denominator equal to 0. When you have a number that doesn't have an x attached to it, it is not a restriction. So we're going to get our restrictions in this case from these two factors. X cannot equal negative 5 because negative 5 plus 5 is 0, and x cannot equal 5 because 5 minus 5 is also 0. So those are your restrictions. X cannot equal negative 5 and positive 5. Now let's talk about removable points of discontinuity. Removable points of discontinuity. Remember, it comes from things that cancel out. So we see x plus 5s cancel out. That means negative 5 will be your removable point of discontinuity. So x equals negative 5. That's also called the hole in the graph. So I'm going to go ahead and write hole in the graph. Anything that cancels out as a removable point of discontinuity, that's the hole in the graph. The non-removable points are what's left over. In this case, I have one non-removable point of discontinuity. That's going to be x equals 5. Okay? And that's going to be your vertical asymptote. So I'll just say VA. So your domain in this case is going to be all real numbers except for those two values. So all real numbers except for -5 and 5, and we'd write it as -infinity to -5, -5 to 5, and 5 to infinity with the u's joining. The vertical asymptote, again, that's going to be your non-removable points. So these things essentially are the same. You would say x equals 5. And your horizontal asymptote, well, we have a little rules, right? So in this case here, if you notice, these are both the same degree, right? So anytime you have the same degree, then the horizontal asymptote is going to be y equals the leading coefficients. So if you look at my leading coefficients, I have, well, that's going to be 1, and that's going to be 2. So 1 over 2 is the horizontal line that that graph tries to look at. And that was the one we couldn't really figure it out. So let's kind of verify that with the graph real quick. Okay, we're going to put this graph back up. And notice that I put 0.5. That is 1/2. So 1/2, same thing. You have that vertical line that the graph tries to touch, but it does not touch, right? It comes close to it on either end. So that is your horizontal asymptote. Your vertical asymptote is x equals 5, as we proved over here. But there is a hole in the graph, and you have to scroll to the left here and find it. And it's not something that comes naturally, right? You have to hover over it and click on it. And you can see that open circle at -5. That's your hole in the graph. So it's undefined there. Can't plug -5 in and get a value. So that's your hole in the graph, aka your removable point of discontinuity. All right, next example. Last example, we're going to write a function based off of the graph. So here we go. On this example, what we're trying to do is we're looking at the graph. We want to be able to identify all the points of discontinuity, asymptotes, holes in the graph, and be able to come up with an equation. And we're going to graph it in Desmos and see if we can mimic that. So the thing I want to start with first is I want to come up with the vertical asymptotes. So if you look on the graph here, you're going to notice that it appears that this line right here is a vertical asymptote. And so that's going to be x equals, and it looks like x equals 0 right here, right? That's the y-axis, x equal to 0. Another vertical asymptote's right over here. We've got x equals 4. So those are my only two vertical asymptotes. So those are two non-removable points of discontinuity. So let's think about what this function would look like. I'll just say like y equals. If they are non-removable points, then x equals 0. That's going to give me a factor on the denominator that's just x, okay? Nothing else. X equals -4. Well, that's going to give me a denominator. So 0 is going to give me x. -4 is going to give me a denominator. And that's going to be x plus 4. Or, excuse me, x equals 4 is your vertical asymptote. So that's actually going to be x minus 4. I almost messed that up, okay? So we have x times x minus 4. And they don't get a numerator because they don't cancel anything from the top, all right? That's just what's left over after you cancel. So you're stuck with those on the denominator. But if you look over here, we have a hole. And that hole is going to be x equals -4. So that hole is your removable, okay? Remember, your removable point of discontinuity is the factor that cancels out. So x equals -4 comes from the factor x plus 4. Remember, this comes from x. This comes from x minus 4. However, if I put x plus 4 here, right, and that was a removable point of discontinuity, then guess what? There was an x plus 4 on the numerator as well. So we have x plus 4 over x minus 4. That's all multiplication between them. We don't need those multiplication symbols, but that's what's going on between those. And let's verify that in the graph. So first thing I want to do is let me get my pen, linking this x plus 4 to there and there, because as you know, when you graph this thing, those would cancel out. So if we're looking at like just from purely a visual point, those are removable, so those would cancel out. So you would get the -4 hole in the graph from that. So let's go ahead and graph that. Your function should look like this. I'm going to clean it up without having all the stuff on it. It's just x plus 4 over x minus 4, x plus 4. Okay, that is what your graph function is. Y equals that information. Let's graph it. Okay, I have this graphed in. I put y equals x plus 4, x minus 4, x plus 4 all in the denominator. The y equals isn't necessary, but I'm just kind of used to writing it in function form. And if you look over here at the graph, it's a replica of what we have on paper here. So you'll see, yeah, it's got a vertical asymptote at x equals 0. That's there. It's got one at x equals 4. And if you zoom in a little bit and you hover over -4, you'll get that undefined hole in the graph point. So everything is there. We got our graph. So thank you for watching this. I hope that you have enough tools in your toolbox to be able to do the practice assignment that's associated with these videos. Again, thank you so much. Y'all have a great rest of your day. And let me know if you have any questions. Leave them in the comments or just ask me and you'll hopefully get a response. Thank you.